All right, so it's time for me to keep going over some induction problems, and this video is actually just going to be going through the 4 that were already in the skeleton notes, so the 4 like official class examples. So the first one that we did in class on Wednesday was to use induction to show that the number 6 to the 2n minus 1 plus 1 is divisible by 7 for all integers n greater than or equal to 1. So again, going back to the idea of what we're trying to do with induction, we're trying to show that for every possible number n that we could plug into that general format, it will always give us something divisible by 7. But, we can't check all of those numbers individually. So what we'll do is we'll show that it's true for the first one. That's our base case. And then we'll show that as long as one number in that format is divisible by 7, the next one will also be divisible by 7. So let's go and do that. So first, we've got the base case. When n is equal to 1, we get the number 6 to the 1 plus 1, which is 7, which is clearly divisible by 7 because it is 7. Nice. Okay, then for the second example, we're going to assume that the number 6 to the k minus 1 plus 1 is divisible by 7. And I guess I can do the thing here where I write it specifically. I don't know, or maybe I won't. Sorry. So assume 6 to the 2k minus 1 plus 1 is divisible by 7. And now the number for n is equal to k plus 1. That's 6 to the 2k plus 1 plus 1. And I get this because here 6 to the 2k plus 1 minus 1 is equal to 6 to the 2k plus 2 minus 1 is equal to 6 to the 2k plus 1. That's how that happens. Okay, so we want to get our assumption to show up. And so what we'll do is we'll factor out 6 squared because by exponent laws, that will reduce the exponent of 6 enough to get back to 2k minus 1. So here we now have 6 squared times 6 to the 2k minus 1, and then still that plus 1 on the outside. And we have 6 to the 2k minus 1 here, so that's good. We almost have, what our assumption is. So let's keep making that show up by doing that little trick where we now have 6 to the 2k minus 1, and we go plus 1 minus 1 within the bracket. Then we now have the entirety of the assumption number, the 6 to the 2k minus 1 plus 1, this whole thing here. And so that's good. We know that's divisible by 7, so we kind of want to keep that together. And then let's look at what we have left over. So doing a little bit of expanding, we now have 6 squared times 6 to the 2k minus 1 plus 1 minus 6 squared, which we can just write as minus 36, plus 1. So that's 6 squared times 6 to the 2k minus 1 plus 1 minus 35. 35 is 5 times 7. And so that means we now have 6 squared times something divisible by 7. That's 6 to the 2k minus 1 plus 1 minus 7 times 5. Both of these are divisible by 7. And so that means the whole thing is also divisible by 7. And so the whole thing is divisible by 7, therefore by induction, 6 to the 2n minus 1 plus 1 is divisible by 7 for all n. Beautiful, beautiful, beautiful. Okay, then for this number 2, I did start this one in class. We didn't finish it. I'm just going to start it over for the most part. I'll keep some of this actually. Okay, so this whole equation is what we call our statement Pn. I've kind of stopped using that because I feel like in talking to students that doesn't necessarily resonate with a lot of you. So, okay, one second. Okay, so what we do here is we want to show, that 1 over x to the n times x minus 1 is equal to 1 over x minus 1 minus, and then now we're just subtracting a bunch of powers of 1 over x. So we have minus 1 over x, minus 1 over x squared, minus, all the way until we have 1 over x to the n. And so the number n that we're using to kind of enumerate all of our different equations that we're trying to prove, the n from the left-hand side just determines how many extra times we subtract powers of 1 over x on the right-hand side. And so, for our base case, we've got on the left-hand side 1 over x times x minus 1. And on the right-hand side, we have 1 over x minus 1 minus 1 over x. And here, because n is equal to 1, we have 1 over x to the 1 is the last term, so we just stop there. Okay, well, let's do a common denominator on the right-hand side. That gives us x minus 1 all over x times x minus 1. So that just gives us 1 over x times x minus 1. Nice. All right, so now let's do our inductive step. We will assume that n is equal to k is true. So that means that 1 over x to the k times x minus 1 is equal to 1 over x minus 1 minus 1 over x minus 1 over x squared minus all the way to 1 minus 1 over x to the k. And then now we want to show the statement for n is equal to k plus 1 is also true. And so that one is, again, just kind of replacing n with k plus 1. So we have 1 over x to the k plus 1 times x minus 1 is equal to 1 over x minus 1 minus 1 over x minus 1 over x squared minus, and we'll have minus 1 over x to the k, but we'll also have 1 over x to the k plus 1 in our big subtraction. Okay, if we do some kind of labeling here, we can call this left-hand side for k plus 1, and then right-hand side of k plus 1. And we want to show these are equal to each other. Now, if we look, right-hand side k plus 1, it looks a lot like the right-hand side for the k case. Right-hand side k is this, where we just go from 1 over x minus 1 minus 1 over x all the way to 1 over x to the k. And so that's how we'll use our assumption. We just have an extra term there. And so if we take right-hand side k plus 1, that's equal to 1 over x minus 1 minus 1 over x. I'm trying to be kind of redundant here and kind of rewriting things a lot just to hopefully make it easier to follow. But if you're ever worried about the amount of work you're showing and if it's okay to skip things, for sure check with me. That's fine. Okay, so the right-hand side for the k plus 1 statement looks like this. And by assumption, we can replace all of those first terms with left-hand side of k, which is 1 over x to the k, x minus 1. So by assumption, this is equal to right-hand side k, which would be equal also to the left-hand side for k. That was the whole point of the inductive step, is that we assume that. And so we've now got 1 over x to the k times x minus 1 minus that extra term we didn't take care of, 1 over x to the k plus 1. So now what we can do is combine these into like one fraction with a common denominator. And so the first term we can multiply on the top and the bottom by x. The second one on the top and the bottom by x minus 1. That should do it. So we've got x minus 1 over x to the k plus 1 times x minus 1. And if we simplify, we get 1 over x to the k plus 1, x minus 1. And if we look up, that's exactly what we wanted for the left-hand side for the k plus 1 case. Amazing. That's what we wanted. And so here we've shown that, the pk plus 1 follows from pk. Therefore, by induction, we can say that, okay, I'll write it all out. 1 over x to the n times x minus 1 is equal to 1 over x minus 1 minus 1 over x minus all the way to 1 over x to the n for all n greater than or equal to 1. And we still need that x can't be 0 or 1, which makes sense. Cool. Okay, so that's that one. Hopefully that's making more sense. Maybe me labeling things a little differently this time clicks for you. I'm happy to show a bunch of different ways to do these if that helps. All right, so example number 3. We want to show that 1 times 2 to the 0 plus 2 times 2 to the 1 plus 3 times 2 squared all the way up to n times 2 to the n minus 1 is equal to 1 plus n minus 1, 2 to the n, for all natural numbers n. Okay, so here we can kind of see that we've got this pattern where for each of these new terms, we're counting up 1, 2, 3, etc. And then each of those has been paired with a power of 2 that's like 1 less than what it is. Okay, sorry, that just cut off. Okay, so for this one, we're trying to show that 1 times 2 to the 0 plus 2 times 2 to the 1 plus 3 times 2 squared plus all the way up to n times 2 to the n minus 1 is equal to 1 plus n minus 1, 2 to the n for all natural numbers n. All right, so here, base case, if n is equal to just 1, we only have one term here, because if we even looked at the last term, that would be 1 times 2 to the 1 minus 1, so 1 times 2 to the 0. So we just have 1 times 2 to the 0. So that's just 1. And then on the other side, we have 1 plus 1 minus 1, 2 to the 1. So that's 0, so we get 1. Okay, we're good. Yeah, I was just thinking if I wanted to explain something slightly differently, but no, it's okay. All right, so inductive step. Let's assume that the sum 1 times 2 to the 0 plus 2 times 2 to the 1 all the way up to k times 2 to the k minus 1. Let's assume that is equal to 1 plus k minus 1 times 2 to the k. Then we want to show that the next one works. Okay, so we've assumed that this is true. We want to show that if we go 1 times 2 to the 0 plus 2 times 2 to the 1 plus dot 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 plus k times 2 to the k minus 1 plus k plus 1, 2 to the k, that should be equal to 1 plus, so k minus 1 plus 1 will just give us k, and then 2 to the k plus 1. And so here again, if we want to kind of label things, that previous equation that we assumed, we can call it as like right-hand side for k and left-hand side for k. And then the new one that we're trying to prove, we can call left-hand side k plus 1, right-hand side k plus 1. Okay. I will say, let's start with the left-hand side for k plus 1 because it looks so much like the left-hand side for k, right? We can match up these terms and we can see that the entirety of the left-hand side of k is contained there. We've just got this extra term. And so let's start with that. So left-hand side for k plus 1 is equal to 1 times 2 to the 0 plus all the way to k times 2 to the k minus 1 plus k plus 1, 2 to the k. So those first terms, let's replace all of them with 1 plus k minus 1, 2 to the k, using our assumption. And then, because that's like right-hand side k that we plugged in. And then we still have that leftover k plus 1, 2 to the k. All right, and then let's see how we can manipulate this. Well, looking at what we've got here, I see that we've got 2 to the k twice. And so let's see what happens if we collect all of those coefficients for 2 to the k. We've got k minus 1 plus k plus 1 times 2 to the k. We've got some simplifying there. So we've got 1 plus 2k 2 to the k, which is 1 plus k times 2 to the k plus 1. And that's the right-hand side we wanted for k plus 1. And so by induction, we can say that 1 times 2 to the 0 all the way up to n times 2 to the n minus 1 is indeed equal to 1 plus n minus 1, 2 to the n, for all natural numbers n. And now we move on to our last example. Oh, this one's a clever one because it's going to use some trig identities. Let's see. Okay. We want to show that cos of x times cos of 2x times cos of 4x times all the way up to cos of 2 to the n minus 1x is equal to sine of 2 to the nx over 2 to the n times sine x for all natural numbers n and for all x not equal to pi k. So no multiples of pi, which makes sense because this fraction has us dividing by sine x, and we don't want that to be 0. So that's all that really means there. All right, so base case. For the base case, we can see that the last power of, or I guess the last factor on left-hand side is cos 2n minus 1x. So if n is 1, then we just have cos 2 to the 0x. So just cos x on left-hand side. We just have like the one term. Okay. And then the right-hand side, for n is equal to 1, we get sine 2x over 2 sine x. Here we can use a double angle identity, replace sine 2x with 2 sine x cos x. Again, that's by a double angle identity telling us that sine 2 theta is 2 sine theta cos theta. And then we can see that we've got 2 sine x canceling out from the top and the bottom, and this is just cos x. Amazing. Okay, so now let's do our inductive step. Let's assume that our product works for n is equal to k. So cos x times cos 2x all the way up to cos 2k minus 1x is equal to what the formula says. So sine 2 to the kx over 2 to the k sine x. Then what we want to do is we want to show n is equal to k plus 1 follows the same formula, right? So we want that cos x, cos 2x, all the way up to cos 2 to the k minus 1x times cos to the 2 to the k times x is equal to sine to the 2k plus 1x over 2 to the k plus 1 sine x. Okay, so now what we'll do is, actually I've been really liking this labeling. Let's call this left-hand side for k plus 1 and right-hand side for k plus 1. Okay, then we also can see that a bunch of these terms match up, or these factors, right? And so we can say, by assumption, the left-hand side for the k plus 1 case is equal to, and just plugging in what we would get if we replace those first factors, we get sine to the 2 to the kx over 2 to the k sine x times that extra little factor we get, cos 2 to the kx. Okay, so now we want to show that this is equal to right-hand side k plus 1. Well, what we'll do is we'll use the double angle identity again, but I'm going to rewrite it a little bit. Here, I'm going to show that if we've got sine theta times cos theta, that's equal to 1/2 sine 2 theta. So just taking our double angle identity and dividing it by 2, and then we can see that we've got sine of 2 theta, or sine of theta and cos of theta, where it's like we're saying our theta is equal to 2 to the kx. Wasn't that cool? So, you know, just plugging things into that formula, we've got, oh, is this an extra example I added? Oh, okay, I guess I'll do that too. Okay, so that means we've got 1/2 sine 2 theta, so that means 2 times 2 to the kx, over 2 to the k sine x. And if we simplify this, that gives us sine 2 to the k plus 1 x over 2 to the k plus 1 sine x. Oh, look at that. That's exactly what we want. That is exactly right-hand side for k plus 1. Isn't that amazing? So we're good. By induction, we can say that, oh, I'm not going to write it all out again. I'm sorry. I'm getting tired. I'm going to say by induction, the identity holds for all n greater than or equal to 1. Okay, and then I guess I gave myself one extra problem to do for fun.